Yeah. Hello, everyone. So we are about to start the session. Please find your seats. All right. So I'm happy to announce the first speaker for the Learning-Augmented Mechanism Design session. So we are going to have Xizhi Tan from Drexel University telling us about Learning-Augmented Mechanism Design, leveraging predictions for facility location, which is actually quite a nice paper. In my own PhD course, I teach the one-dimensional version that I learned from Eric Balkanski. So I'm so looking forward to know more details about this work. So with that, the floor is yours.
Cool, thank you. Hi everyone, my name is Xizhi Tan. I'm from Drexel University. This is a joint work with Priyank, Agrawal, Eric Balkanski, Vasilis, Gkatzelis, which is my advisor, and Tingting. So kind of like in computer science, the way we approach problems basically could be separated into two types. You either have this traditional algorithm design that gives you the worst case guarantee, which, it provides robust, guarantees. However, they are kind of like defined on this single worst case, sometimes could be overly pessimistic. And on the other hand, we have these beautiful machine learning-based heuristics, which they focus, they really want to do good in practice. So they are very efficient, but most of them do not have any non-trivial worst case guarantees. And in this recent line of work of learning-augmented algorithm design, where they're trying to trying to get the benefit from both sides by designing algorithms that takes into some prediction and trying to achieve the bounds, sort of like the best worst case guarantee together with, in practice, good performance. And in our work, we try to extend this to beyond algorithm to this mechanism design world, which we found is like very natural extension. However, to the best of our knowledge, no prior work has considered this. So if there's anything I want you guys to take away, it's very early in the talk, but it's the fact that we want to do learning-augmented mechanism design. Okay, so before I jump into any details, I just wanted to get you guys more familiar with this learning-augmented framework in the algorithm design world. So like I said before, this recent line of work assumes that when you are designing the algorithm to your problem, it has access to a prediction regarding the instance. Notice that kind of like one of the benefits for this framework is that we have no assumption regarding the way the input is generated, which is like necessary for a lot of other analysis model like distributional analysis. And then the goal for this framework is that we want to achieve optimal or near optimal performance when the given prediction is correct, but at the same time, we still want the existing best, worst case guarantee. It is very important because we're not losing what we want in the worst case, but still do better. So a lot of the previous work has focused on online algorithms, where the information, it has this information limitation that you don't see the whole instance at the very beginning. Like the instance arrives online and the algorithm needs to make an immediate and irrevocable decision giving this partial instance. And they use prediction exactly what if this is provided with a prediction on this partial instance that is going to arrive in the future, which you don't have. And taking this prediction, they're aiming to achieve better competitive ratio when the prediction is correct, and also guarantee the worst case. I feel like I've been repeating that so much. But in the framework, the two performance metric that we consider formally is defined as consistency and robustness, where you can think of consistency as the ask that I want to get when my prediction is correct, and the robustness is the worst case competitive ratio overall. And one thing I'd like to point out here is that the robustness is essentially the standard notion of worst case guarantee. We're saying no matter how wrong your prediction is, you still need to obtain those guarantees. So in our work, we extend this framework to mechanism design problem, where the difference between a mechanism design and online algorithm, so to speak, is the fact that the information limitation is different. We're not we have all of access to all of the agent's value. However, the agent's values are private. And even worse that the agent are strategic, they would actually misreport strategically for their own benefit. So the mechanism needs to elicit the true values. Now, given this information limitation, we ask the question of what if we have a prediction regarding the agent's private informations? Can we use this prediction to get kind of like the same guarantee that they achieve, good consistency with robustness? And when you cannot get the best of both worlds, can we design a mechanism that is as close as possible to this best of both worlds ask? So I guess the central question we ask in this paper is that, can learning-augmented mechanism achieve good robustness and consistency trade-offs? So for the rest of the paper, I'm going to showcase this mechanism design with prediction framework using the canonical facility location problem. But kind of like, this is the framework that I want you guys to take away. And basically, we think there's like a lot of exciting open problems in this field. You basically can ask like with prediction framework with all of the mechanism problem you like to kind of like overcome the existing impossibility result. But with that said, let's jump into facility location and see the power of prediction. So just to remind everyone, the setup of facility location, we consider the single facility location problem where we have n agents on the two-dimensional Euclidean space. We need to choose one single facility somewhere on the plane. The cost of each agent is defined as the Euclidean distance from his location, preferred location to the facility. And our goal is to choose a location such that we minimize some sort of social cost objectives. In this paper, we consider the egalitarian social cost, where we're trying to minimize the maximum distance. You can think of this as more like a fairness notion that we don't want the facility to be too far away from any of the agents. We also consider the utilitarian social cost, where we're trying to minimize the average cost. Both of them are kind of like standard notion people use in facility location literature. And so far, this problem is a purely algorithmic problem. Now, the mechanism, the strategic part comes in where the fact that agents' preferred locations are private, and agents will strategically report the location, aiming to minimize their cost. Now, let's see what we can do without prediction, using a very simple warm-up case in the single dimension for egalitarian social cost. So again, egalitarian is trying to minimize the maximum distance. And if you think about the case in one dimension, the optimal solution would be to output the points in between the leftmost point and the rightmost point. However, in mechanism design world, if we just take agents' input and output this algorithmic optimal solution, it's not strategy proof. And a very simple example we can see is that if you are the leftmost agent, one thing you could do is you can report a location that is further to the left. In doing so, you actually drag this outcome to the left, which is closer to your actual position. And in fact, we show that, not we show, but like previous work has shown that the optimal is not achievable truthfully. And if you want to guarantee truthfulness, the best you can hope for is a 2 approximation. And outputting the median or any order statistic can give you this 2 approximation. So the question we ask in the paper is that, can we beat the 2 when we're provided with a somewhat accurate prediction? Now, before I answer that question, we didn't even discuss like, what is the prediction? Like, what's this extra bit of information that is provided to the mechanism? Well, you can have a prediction of the whole instance, like everybody's preferred location, but that's like a lot of information to ask. So in this paper, we consider actually another version. We assume that the mechanism is provided with the one single location, that is the predicted optimal location. It's like a lower dimension, it's like easier to learn. And if you provided with this prediction, if you think about it, it's actually very easy to achieve one consistency. You should just always output the predicted location. And then when your prediction is correct, you get the one consistency. However, it's very easy to see that this gives you unbounded robustness, because what if everyone is like in the side of the class and you choose to go to track B or track D or something? So the ask in our paper is like, how can you, get this one consistency because it's really good, but at the same time provide it with me some like non-trivial robustness guarantee. And we actually proposed this mechanism called min-max-p that is strategy proof, of course, and one consistent and 2 robust. So kind of like just to explain this result a little bit further, that means we get the best worst case guarantee. Our mechanism is just as good as any truthful mechanism can do. And on top of that, when we're provided with a correct prediction, we always output the optimal. The way we achieve it, kind of like give a high level idea, is very simple. We take this predicted optimal, and if the predicted optimal is in between the reports of agent, we simply output this optimal location. If this optimal location is outside of everyone's range, we find the closest points and we output that point. And like I said before, it kind of like simultaneously achieve the optimal consistency with the best robustness. We call this like the best of both worlds, which is like the optimal scenario for mechanism design framework. Now, let's take this and move on to second dimensions, again with the egalitarian social cost. Without prediction from the previous result, we know that the best you can hope for is a 2. And in fact, if you output the median on both of the directions, so if you take the median on the x-axis, and if you take the median on the y-axis and you output the crossing point, that actually gives you the 2. And we ask a similar question here, is that can we beat the 2 with prediction? And the answer is yes. We propose for egalitarian in second dimension, we propose this minimum bounding box that is strategy proof, 1 consistent, and 1 plus root 2 robust. So as you can see now that we no longer have the best of both worlds, as the robustness we achieve is slightly worse than 2. But in fact, we show that any deterministic strategy proof mechanism that is better than 2 consistent is no better than 1 plus root 2 robust. So what does that mean? That means if you want to use any like prediction to achieve anything better than a 2, like if you want to use the prediction, because you can always ignore the prediction and always get a 2 consistent. But if you want to use the prediction and get anything better than 2, the best robustness you can hope for is 1 plus root 2. So in other words, our mechanism is the best trade-off between consistency and robustness. Again, similar as before, just some like high-level intuition. The mechanism we have for this one is basically an extension of our mechanism in the previous scenario, where we first find the minimum axis parallel bounding box of the points, and then simply ask the same question. If the prediction is inside the point, we output the prediction. If the prediction is outside of the points, we output a point that is closest to the prediction. So the high-level idea of how do you strike a balance between consistency and robustness, for me personally, is the fact that especially for this type of question, facility location, there's a lot of outcome that would give you the robustness you want. Like any order statistic in single dimension gives you this 2 approximation. And in fact, any points in this minimum bounding box would give you this 1 plus root 2 approximation. And then we're just using the prediction to guide us towards one particular outcome that gives you good consistency at the same time. And then one person may ask, consistency is kind of like a guarantee that is not that realistic, because like how would you get a machine learned prediction that is 100% or exactly correct? How could you get a prediction that's exactly at your facility, like optimal facility? So to kind of like address that issue, we actually have the result of this minimum bounding box approximation as a function of the error, where the error is defined as the distance between the actual and the predicted location normalized by the opt. So even if your prediction is not exactly at the optimal, as long as it's relatively close, like it has some like reasonably accuracy, we still gives you good kind of like performance. And it's as long as it's like always upper bounded by the robustness. So no matter how wrong your prediction is, it's always bounded by the robustness. Now, move on from egalitarian to utilitarian. So just wanted to remind everyone that utilitarian social cost is aiming to minimize the maximum, the average distance between everyone. So without the prediction, the prior work has shown that no deterministic strategy proof mechanism can achieve a robustness better than square root of 2. And then the coordinate-wise median that we just discussed actually achieved this square root of 2. And for us, we propose a mechanism, this one is a bit more complicated, called coordinate-wise median with prediction that is provided with this confidence parameter C. And then we achieve, I know it's very hard to read the math, but we achieve that consistency and that robustness. You can see the consistency, the green line, and the robustness as a function of the parameter. So kind of like to interpret this result a little bit, you can think of this confidence C parameter as your confidence towards the mechanism, towards the prediction, sorry. So we provide with the mechanism designer kind of like a whole family of mechanism, depending on how you feel about this prediction. If you not really sure about this prediction, I don't know if I should use it, you can set the C close to 0, which will actually restore the best you can hope for any worst case mechanism. And if you are really confident with this prediction, you think it really works, you can set a C that is very high, like close to 1, which gives you close to 1 consistency. So you're always achieving like the best thing that you can. And similarly as before, we show that what we're achieving right here, even though all of the consistency comes with the loss of the robustness, this is the best, again, best trade-off that you can achieve. So you can think of this graph on the bottom right as the Pareto frontier of the consistency and robustness given this prediction. And I guess I don't have time to go through the actual mechanism, but this mechanism basically add Cn phantom points, where C is the confidence parameter, and then run the coordinate-wise median. And we also, for utilitarian, get the same result in terms of arrow that strike like gracefully deteriorates between consistency and robustness that we achieve. So kind of like to summarize this paper, in this paper we introduce this learning-augmented mechanism design framework, which we believe there's like a lot of open problem to this. And basically the whole framework says, for any mechanism design problem, you identify the information limitation. What is causing this mechanism to do bad, besides strategy proofness, of course. And then you have this prediction that kind of like help the mechanism to overcome the pessimistic impossibility result. The hope we want is that we want both good consistency and robustness at the same time, where we're basically trying to guarantee that if the prediction is correct, we do optimal. If the prediction is wrong, we do still get the best, the worst case. When it's impossible, we strive to achieve the optimal trade-off. And we get that for facility location problem, we get the following result, where egalitarian, we get the best of both worlds, and for both egalitarian and utilitarian on second dimension, we achieve the optimal trade-off between them. So again, like you can ask the same framework to any of the mechanism design problem that you like, and then like with the existing impossibility result and ask the same question. What prediction makes sense here, and how can you use it to overcome this? And that concludes my first talk. Thanks.
So we have time for a few questions. It's better if you go to the podium to that microphone and ask your question there. But if you have a loud voice, you can just.
Thank you. Yeah, thanks. Very, very nice, interesting result. So I guess my question is about, is your mechanism determined by the deterministic space of the mechanism? Or
Yeah, our mechanism is deterministic.
Yeah, so do you have any intuitions on how does like randomized algorithm make the same different?
So, so the mechanism that we use for this particular problem, and then the result we get, kind of like heavily depends on the characterization for this voting scheme provided by Mulan, which is like, so that's why the deterministic is like important here. We didn't discuss the randomized algorithm in this particular question that this paper is focusing on, but that's like definitely interesting.
Okay.
Yeah.
Yeah. That's right.
Is it too tall?
That would actually come out. Yeah. No. Okay, it's really just passing that for me. Hi, so for the egalitarian in R2 mechanism that you proposed with the minimum bounding box, when I think about extending Euclidean distance into higher dimensions, just from 1 to 2, I envision it going from, you care about distance in a line to distance in around circles of sorts, that you might want to create like a bounding circle of some kind, and if you're outside of the circle, you project onto it instead of using a bounding box. Is there a reason why when we kick it up to R2, you use a bounding box as opposed to a bounding circle of some sort?
So I think the circle is absolutely, like if you, let me think. Well, the box we defined is definitely inside the circle, if you think about it. So like the way we think about it is like if you, I think the circle would also work, and I think it probably provides the same approximation ratio. But what we're trying to do here is like, we're trying to have this range where it provides like a good robustness, and we want the range to be as small as possible, because like the tighter it gets, like weakly the robustness should be, and then within this range we want to use the prediction to guide it. That's why we use the square. And then for the question of moving beyond multiple dimension, if you use, you can extend this to multiple dimension as well. You have the higher dimension minimum bounding box, but that doesn't give you that good of a like guarantee. It gives you root d, 1 plus root d to be specific, where d is the dimension, where you can achieve a 2 using the median algorithm. So that's still wide open. Like how do you use this prediction in higher dimension is a very open, interesting question. Yeah.
Gotcha. Thank you.
Mm-hmm.
All right. So in the interest of time, we're going to switch to the next talk.
It's okay. That next talk is also me, so you can ask questions.
You can ask your question offline if you don't mind.
Yeah.
Sorry about that. All right.
So should I?
Yes. No? Yeah.
Can I still ask?
Yes, go for it.
Oh, okay. Sorry. So, given that the title has learning in it, could you help out the statistician and clarify if the prediction is actually a confidence interval? I'm not saying the mechanism needs to be randomized, but if you actually output, let's say a 95% confidence interval, would you have a estimated, expected approximation factor that can be lower than 2? Because you can imagine the confidence interval covers some of the worst case.
That's a good question. So in our case, the reason why we have this like deterministic and this single bit of information is we're trying to have as least assumption as possible. We don't have any assumption in terms of how correct your prediction is. It's more kind of like this is an extra bit of information, and we're trying to take use of it. And then I agree, it's kind of like out of our control how good this prediction is, but we're trying to give you like a range in terms of your approximation ratio that is lower bounded by the worst case. I would say it's very interesting to kind of like consider if, like you said, if this prediction, I have some confidence in terms of how correct this prediction is, and given that, combined with the algorithm to give you like an expected worst case guarantee, but that kind of like deviates of what we're trying to achieve here, because it's trying to, in practice good and also in worst case good. So we really like the robustness side, but I think that's like a good question to ask, because we don't really have any assumption in terms of how the prediction is generated, and then we only know, kind of like we only discuss how do you use it without hurting your robustness.
That makes sense.
Thanks. Yeah.